In this slide, we'll introduce the synthesis equation, and we want to view the synthesis equation from the matrix vector product point of view. The DFT synthesis equation looks like this. Xn is equals to 1 over n, where n represents the number of elements we are going to analyze, and it is a sum of xk, which is the DFT coefficients, multiplied by this yellow element here, which is ej 2 pi over n kn. So what we need to do is that we plug in a value of n. So for example, we start with n equals to 0, and then this little n will be equals to 0, or here equals to 0, and we have to iterate over k from k equals to 0 to n minus 1. So we are iterating x of 0, capital X of 0, capital X of 1 until capital X of n minus 1, multiplying by this complex exponential value, again iterating over k. So just to calculate one element of xn, we have to do n multiplications, and of course we have to repeat over for n equals to 0 to n minus 1 for n element, and that's why this analysis takes n squared operation. Now let's put it as a matrix vector product. Let's examine x of 0, so we put x of 0 here. X of k, we put it here. And remember, a matrix vector product means take this row and multiply by this column to get the first number. You realize that each entry of this is simply the elements specified by this notation here. And for how we are iterating across the row, this row along the columns is from k equals to 0 to n minus 1. If you plug in all the values, you will see that in the first row, because n, small little n equals to 0, all the entries have value 1, because it's ej 2 to pi divided by capital N, k times 0, everything is 1. The second row is more interesting and visually more exciting. Remember that here we are moving along k, and here this row, it is n equals to 1 associated with this element n. N equals to 1 is constant. Therefore, the only thing that is moving is k, as we are moving across each column. K equals to 0, k equals to 1, k equals to 2, up to k equals to n minus 1. So now you can fill up this whole matrix. When you fill up this whole matrix, now let's interpret this equation, analysis equation, from the point of view of orthogonal decomposition. This is U0, U1, U2, U of n minus 1. Where what is U? These U's are the U that we have talked about in the previous slide, the orthogonal basis. This is the Fourier basis U. What is C1 to CP? This is the capital X, the DFT coefficients. If you check the U's, they are orthogonal. That means when U0 dot with U1, you'll be 0. U0 dot with U2, you'll also be 0. U0 dot with U0, it's not. I explained it as 1 in the previous slide. I shouldn't say that. I should say it is not equals to 0. It will be equals to the norm of U1 square. Okay? And in this example, later on you will realize that the norm would be Now, with that, you've already understood it from this notation here. X in time is equals to 1 over n times a matrix WH multiplying by the DFT coefficients represented as a column vector. The next slide will show you that WH and 1n has an inverse. This guy has an inverse called W. And the W is the famous DFT matrix. Thank you.